All right, number 14, we want to place a $50 nickel and a quarter, $50 and nickel in the position that we see, and want to try to move the coins one at a time from position C, from A to C, and at no time may a larger coin be placed on a smaller coin. And it says we can put them in position B. How many moves will it take to get them to C? Okay, so there's actually a pattern here. There's a formulation that we can use. I kind of want you to see what's going on, so I'll actually do it here for you. I don't remember seeing it in our text. It may be there. I might have overlooked it. Let's just call this A, B, and C. I'm going to use a quarter, nickel, and a dime. Show you what it is with 3, 2, and 1, and then try to show you the formula. All right, so if these coins were here in position A, got a quarter, nickel, and a dime, and I want to move them all to C without putting a bigger one on top of a smaller one, I can do it by moving 1, 2, 3, 4, 5, 6, 7. Takes me 7 moves to move from A to C with 3 coins. What if I had 2? 1, 2, 3. Would take me 3 moves. And if I only had 1, it would only take me 1 move. So where's the pattern between these numbers? What's going on? What's happening? What's being counted? All right, so from here to here, difference is 1 plus 2 gives me 3. Difference here, 3 plus 4 gives me 7. And if we had 0 coins, it would take us 0 moves. So the difference from here is 1. Where's the pattern? We start with 0, we go up, count by 1, we get 2. It doesn't look like there's a pattern. The next one would be 8. What's happening is this number is being doubled. Take this times 2, you get 1 times 2, you get 2. 2, multiply that by 2, you get 4. 4, multiply that by 2, you get 8. And so the next time it would take us 15 moves. And we can keep going. When you notice this, that there is a doubling, or you take this number, double it, and you get the next number, that's the difference. That's a power rule. So we're looking at powers of 2. One of those power functions. So we're looking at this. 2 to the 0. 2 to the first. 2 to the second. I'm using these numbers up here as my 2, 1, 2, 2, 2, 3. So forth and so on. However, if you raise 2 to the 0 power, this is giving us 1, not 0. If I raise 2 to the first power, this is giving me 2, not 1. If I raise 2 to the second power, it's going to give me 4, not 3. If you do this, though, you notice the difference in each of these is just 1 less than what we're getting. This is 1, we got 0. This is 2, we got 1. So if we take this number and subtract 1, and this is a very popular formula, this is something we use to get subgroups in statistics, or how many subsets. This is what we want to use. So depending on how many coins I have, if I take that number and then I subtract 1 from the result, 2 to the n power minus 1, that will tell me the number of moves. This is a formula that's going to help us to solve this. So in this case, we have 2 to the third. It's always our base 2. We got 3 coins. Subtract 1. That will give us 2 times 2 times 2, which is 8. Or I can also punch that into the calculator. Just show you. 2 raised to the third power gives us 8, and then subtract 1 gives you 7. So this is a formula that we're going to be using to find out how many moves it would take me, depending on how many coins I had stacked up, to move them from one position to the other without putting a bigger coin on the smaller coin. Okay, so for this one, we would say it's going to take us 7 moves with these 3 coins. And then part B wants us to generalize this. If we had a pile of 64 with decreasing size, after how many moves or how many seconds would this end? And saying assume it takes 1 second to make a move. So the formula that we would need would be this one. If we had 64, we would take 2, raise it to the 64th power, and then subtract 1.